Yes, here we are. It's the physics video lecture. Physics 203, video lecture 26. We've been doing fluid mechanics with the intention of studying the wave equation. So that's what we arrived at last time. And for these last couple of lectures and this one and the next one, there won't be any homework problems assigned. So let me encourage you to make your notes really good. You're only going to get this material in this form right here, and it's going to go interesting places. So yeah, just work on your notes, leave a lot of space, fill in every missing calculation, every missing thought, and you'll really have something for your efforts. Good. So let's see. Let's say fluid mechanics, fluids to wave equation. Okay. So that way we can write down what we started with, namely, we'll just say we had the continuity equation. I'll write them all down. Divergence of rho v. Then we had conservation of mass. Then we had the Euler's equation, dv dt, that's a v, plus v dot grad applied to v minus 1 over rho gradient of the pressure. And then we actually just used the entropy is equal to constant. We didn't use that differential equation that goes with that, we just used the constant of the entropy. So yeah, what we did with these equations was we linearized, so love to number things. Okay, one. And then the second step was to linearize the equations. So that assumes that this second order term is small and vanishes with respect to the others, that the velocities are already small, and that the density and the pressure both fluctuate around a constant value. So linearization V is small, P is equal to P naught plus P prime, where that's the small fluctuation, rho, same thing. And what we then obtain is the wave equation. We get d squared phi, and we get the wave equation, first of all, for the velocity, the pressure, the density, but then we get it for the velocity potential. So that's what I'm going to write down, d squared phi dt squared c squared del squared phi. Phi equals phi of x, y, z, and t. That's the wave equation. C is dp d rho, evaluated at constant entropy. You know, I could put a rho naught there, but that's clear. It's evaluated at constant rho naught and constant entropy. So we've got the square root of that. We have v is equal to the gradient of phi, and P is equal to minus rho naught d phi dt, minus rho naught d phi dt, and that's that P prime, the small density fluctuation. So that's how everything is connected, and pressure and density we saw could just be connected as linearly dependent on each other because they're small quantities. So that's fairly complete. Okay? And what we're going to do next is just study some very standard wave equation results that you've seen before, but we're going to be complete about everything we're doing. So good. Oh, actually, add a little bit more to this board. What we had also found was that we had actually solved this, so for phi is equal to phi of x minus ct, which was a plane wave moving in the positive x direction. The fact that we derive our velocity from this as this gradient showed us that we have longitudinal waves. So, plane waves, we find that these waves in a fluid are longitudinal waves. Waves are longitudinal. So there we had a actual physical result out of all this formalism. Something new. Okay, good. There's the complete set of what we have to work with right now. Our next step is to talk about monochromatic waves. By numbering things, why not? So monochromatic and we'll set up the monochromatic waves by writing phi is equal to phi0 of x, y, and z, and then we'll just have the exponential e to the I omega t, e to the minus I omega t. Yeah, if we set things up like that, and we have our wave equation here, then our two time derivatives give us minus I omega squared phi, and that will be equal to c squared del squared. Actually, we can go ahead and write phi naught del squared phi naught, because the time dependence, of course, cancels for both sides. And that'll leave us with a minus sign. So we'll end up with del squared phi naught is equal to minus omega squared over c squared phi naught. And now if we just go ahead and take, again, phi just as a function of x, monochromatic plane wave. So if phi naught is just phi naught of x, just that one variable, then we have phi naught of x is just some constant e to the I omega over c x. And now we can construct the, right, so two derivatives minus omega squared over c squared phi naught. Okay. Two spatial derivatives. We're just taking the one x spatial derivative here. So now we can put these together, and we end up with phi of x and t is some constant, e to the I omega over c, and then we have x, and then here we can have minus ct. Yeah, c cancels these on the side of omega t. So there we go. So this is a monochromatic plane wave, and what did we have here? Yeah, function of x minus ct, it still is, okay, but now through sinusoidal dependence there. Now this was for one dimension, just in x, but we can trivially extend this to 3 dimensions and have the same thing. So that's what we'll talk about. That's what we'll have. We'll extend this here. And I actually have a this is also known as the wave equation. All right, so this is always the wave equation, of course, but this, under these circumstances, also referred to as the wave equation. We'll come back to that. Good, so let's see here. What we're going to do is define the wave vector. So next, we want to extend this to all 3 dimensions. So what we'll do is let this vector k, let vector k be omega over c. That's its magnitude, and the direction is a unit vector. Okay, so n is a unit vector. So now what we can do is just plug this in here, and we'll get our, anything else? Yeah, we can go straight to there. Then we could have phi of r and t, so vector r is equal to a e to the I, and now we'll put that k in there, k dot r minus omega t. And you'll see this is doing the same thing in 3 dimensions that this thing does in 1 dimension, because the k is omega over c. The direction dotted into whatever point you are in space gives you this form as the projection. Okay. So here, let me get a better box for this one. K dot r in 3 dimensions. So that is our monochromatic wave. It is propagating in the direction k, right, which is specified by whatever direction this n hat has. Okay, let's see now. And we're going to name this thing star. And because of this e to the I, we can expand any plane wave as a Fourier expansion of this. So we could do a Fourier integral of this phi here, and then we would have an arbitrary plane wave. So that we're going to write down as well. Note star any plane wave expressed as a Fourier expansion. Okay. So that's the general form. So we also want to get a couple of relations now with the sound speed and the wave vector. So continuing here, good time to do another number. So continuing with this, let's just square this equation. So next, take k equals omega over c n, and we square it. Okay. So we would have k squared equals omega squared over c squared. Now this n squared is just equal to 1. So we can also write kx plus ky plus kz, all those squares is just equal to omega squared over c squared. And we can now solve for omega of c. Omega of c and k, watch this, omega equals c square root of kx squared plus ky squared plus kz squared. So of course this is just a three-dimensional generalization of the expression that you know for linear waves, omega equals c times k. But we can look at this a little closer now. And this c here, what is that? Well, c, since that is equal to the root of dp d rho at constant entropy, this can actually be seen to be a function of the position. We're just treating it as a constant, and rightly so, but it's more than just a constant. So up until now, I'll put it this way, up until now we've just been treating it as a constant, but in fact it can be thought of as a function of the position as well. Of course, in that case, your differentiations would be more complicated, okay? If it were explicitly a function of position. Nonetheless, if we look at it that way, and we will explicitly later on, so I'm just kind of drawing attention to something that's going to happen. This would give us omega being both a function of r and k. And in that case, d omega dk and partial omega with respect to k. So if I say partial with respect to the wave vector k, then that's, you know, it's like a gradient, three derivatives, and that would then be c times this object with respect to x, y, and z, and that's just going to be k vector over k magnitude, just the unit vector, just the way when you're doing the gradient of r, okay? Just a different letter, which would be c, and we would have omega over, you know, I'll even do it explicitly, omega over c, omega over c, which of course is going to cancel, and we'd have an n hat. And so this would be, is down here, d omega dk is equal to c in the n direction, in the direction of the wave vector. And this is in fact true for these general expressions here as well, and this is referred to as the group velocity. So this is actually the definition of the group velocity. I'll put that as an interesting aside here. I'll put it this way, C group velocity. I have a derivation of it in my notes, but I think I'm gonna leave that up to you if you need it. We may need it, we may get it later, but right now, formally, we have it already. So group velocity That's how group velocity is defined. If you have an omega as a function of the wave vector k, then the derivative with respect to that vector, so the gradient, so to speak, is the group velocity, which we see for these monochromatic waves is just the wave speed itself. Okay, so that's a worthy little detour, and we'll come back to this construction later on as well. We're going to go back to this and look up another class of problems here. Yeah. So group velocity, we can either do the derivation discussion of it later, the other one, or you guys can look it up and insert it into your notes, or maybe you've seen it, maybe you haven't seen it. I think you've probably seen it before. Okay, so what's next on our plate here is, I have a bunch of topics here because I have a whole fluid mechanics semester, but we have to pick out the important applications. Good, so what we have next is waves in a bounded medium. Okay. These here we're thinking of just an unbounded space. Okay, they propagate like this. So what happens when it's a bounded medium? I'm tempted to leave this up here and erase this up there, because everything we need is up there. Good. And we'll set up the example that we're going to do right away. So waves in a bounded medium this is where we would start talking about acoustics and musical instruments and other things like that in fluid, we're talking about fluid mechanics. So our example is going to be just inside a box, a cuboid, a box, A, B, C, that kind of thing. So before we get to that, let's look at what the wave equation, how it's going to have to be treated. So we're going to compare in an unbounded medium which is what we're talking about up here. So in an unbounded medium, any frequency is a possible solution of the wave equation. Any frequency omega is possible. In a bounded medium, you're going to get a discrete set of frequencies omega. So here, actually not in the unbounded medium. In the bounded medium, so in the bounded medium, which I'll draw a bigger picture later, but in this box here, in this cuboid, we have to consider boundary conditions. So our wave equation has to solve, our solution to this wave equation has to include the boundary conditions. So consider boundary conditions. And we have the boundary conditions from the Euler equation. Namely that V dot n hat, where n hat now is the normal surface normal, not the wave vector there. Equals 0. Okay. So basically v dot n hat equals 0. And as a result of that, if we begin with these solutions up here, we have to take linear combinations of those equations that are capable of satisfying the boundary conditions. So we're going to begin with phi is equal to phi naught x, y, and z e to the minus I omega t. And then we have to satisfy the boundary conditions, and that'll basically be with a combination of these that turns our exponential functions into sinusoidal functions, sine or cosine. So put that into words, symbols. Yeah. I'll just even write this. A e to the I omega t plus b e to the minus I omega t. So you choose A and B such that we end up with cosine of omega t. Easy enough to do, right? So then we go ahead then we go ahead and say, good, let phi equal phi0 of x, y, and z times a cosine of omega t. Or we could have sine of omega t, and we can of course add a phase to go between the one and the other. So we'll just say cosine omega t, because that's going to be the quickest way to our solution. Make sure I said enough here. Yeah, so we have to be able to satisfy this condition at the boundaries, of that box. So that's why we're doing what we're doing. And of course, you can't do that with this pure traveling wave here. So we end up with this trial solution, and we'll go ahead and set up this box here and see what happens. So we're going to have this cuboid, as we said. We've got a box. I'll draw the box first, and then we'll label X, Y, and Z. The idea is got A, B, C, okay, and we're calling that X, Y, and Z. And we're going to set up this problem here as a bunch of cosines. So A cosine kxx, cosine kyy, cosine kzz, and we already have the cosine omega t. And we go into our wave equation. L squared v naught plus omega squared over c squared v naught equals 0. Okay. Yeah. Good. So what do we get here? del squared, we're going to get two derivatives. We're going to get kx squared, and then with y, we're going to get ky squared. With z, we're going to get kz squared each time. Each time with a minus sign. And of course, the time derivatives gave us the minus sign here with the omega squared over c squared. So we have kx squared plus ky squared kz squared as before. Okay. Omega squared over c squared. But now we have to take into account the boundary conditions. So remember, the gradient of phi, which is right there, is the velocity. So v sub x is equal to d phi dx, and we get a minus a kx sine kxx. You know, I'll write everything out, because we only have to do this once. Ky cosine kzz plus omega t. Here's the thing is, this has to vanish at the boundary of the box. Okay. So if this is a equals 0, and this is, or if this is x equals 0, and this is x equals a, then this has to vanish at those 2 points, and vx of 0 equals vx of a equals 0. It's the boundary condition. So that tells us that kx times a is going to be some multiple of pi. So kx times a, and I'm using m as an integer, is m times pi. M is just an integer. And the same argument is going to hold true for ky and b, kz and c. So we have this ky b is equal to n times pi, kz times c is equal to l times pi, and n and l are also integers. I'll just put them all together. M and l are all integers. Okay, what else are we going to say about this? Got these 3. And we'll just solve for omega squared now. So starting it back at the top there, we have omega squared is equal to c squared times, and our kx squared is going to be pi squared. We can actually factor out a pi squared. So we're going to have m squared pi squared over a squared, etc. So we pull out pi squared, we have m squared over a squared plus n squared over b squared plus l squared over c squared. So there's our relation that tells us all of the discrete possible frequencies of our waves inside this box here. So those are standing waves inside that box. So these are the discrete frequencies of the standing waves in the box. So the possible discrete frequencies. of our standing waves. In the cuboid, in the box. Good. Anything else to say on that one? That's really an important example. So now we see in an unbounded medium, we had the traveling waves, omega squared, c squared, k squared. And we essentially have the same thing, but these are now the discrete frequencies because m, l, and n are integers. So that's for the bounded wave, solutions to the wave equation to bounded medium, perfect example. And we had the unbounded one as well. See how we're doing time-wise. Okay, fantastic. So now, yeah, there would be many, many things to study here. Different boxes, and then you could extend this to what's going on in music, pipes, open and shut, standing waves and pipes and so forth. So some of the things you may have seen, but you get discrete frequencies in all those cases. So we have to move on into, where is my next topic here? Excellent. Well, I'll just put here for a note, for some notes, just you can add stuff or just to be aware of it. You have standing waves, and pipes, etc. Once you have a circular cross section, you have a little more work getting your frequency relations. But if you have a square cross section, a rectangular cross section, you're using these kind of, this would be one of those examples. Depending on whether they're open or not, you have different boundary conditions. And then you're talking about production of sound in musical instruments as an example. So you have that. I also have, as a topic that I'm not going to do here, is reflection and refraction. We're going to come back to that. Of sound waves. So at the level of the wave equation solutions, you can show that Snell's law holds true. So let's just write your reflection. We're going to pick this up later in a slightly different connection. You can do it with the wave equations too. You probably have done that in electricity and magnetism. So, but reflection, you'd have proof that your angle of incidence equals your angle of reflection. And for refraction, you'd have Snell's law. And that can definitely be shown for sound waves, just as it's done for light waves. And I'll just go ahead and remind us, we would have theta 1, theta 2. Now, N1 and N2 for index of refraction, but we're talking about sound waves and not light rays. And so what we would have here would be 1 over C sub 1, and here we would have 1 over C sub 2. That is to say, if we had different wave speeds, across this interface, two media, then if we had different wave speeds, C1 and C2, then we would get a Snell's law. Okay, we'd get refraction at the interface. So that would be refraction. Let me write that a little nicer. we'll actually make that up in a surprising connection later on. Okay, so yeah, those are topics that one could insert here. Okay, that's where we would study them when we have our wave formalism. So our next topic is going to be what is referred to as geometrical acoustics. I've already indicated it with this picture here, namely when you make a transformation from a wave picture to a ray picture. You know that from optics, you've got ray optics as opposed to wave optics, and we actually have the same thing here in acoustics. What we've been doing here is acoustics, okay, because it's sound waves. Good, so let's tackle that. I gotta make sure I don't leave anything out. So this topic is called geometrical acoustics. And it's something you've at least heard about in terms of light. So note, in electricity and magnetism, that's supposed to be an M. Electricity and magnetism and optics, we have wave optics and ray optics. Okay? We have waves and rays. Okay? And in fact, the difference between these two is usually just kind of sketched and not even that rigorously derived. So it's a good time to talk about the subject. Okay. So what do we have here? Let's say we're going to begin with our plane wave solutions to the wave equation. And I'll draw a nice little picture. First of all, we know it's E squared dt squared c squared L squared phi, both sides, wave equation. You know the solution, phi of r and t, a e to the I, k dot r minus omega t. That's a monochromatic wave pointing in one particular direction. And thus far, A has been constant, K equals omega over C, N has been constant, and omega itself has been constant. So A, K, omega, all constant. And the picture that goes with this is like so. So we'll just make this the direction of propagation. So this is our K vector direction. And these are wave fronts. Did I put an origin? Well, let's just say K dot R minus omega t equals 0 when t is equal to 0. Okay, so we could say that's the wave front for t equals 0, and k dot r is all the, k is this direction, r are all the vectors that give us this perpendicular wave front. K dot r equals 0 when t is equal to 0. So k is in this direction. The dot product, knows all the r's in that plane there. So that's what satisfies that equation. So then if that's t equals 0, this could be another time. I'll just say t equals 1, t equals 2, etc. Right? That's that front propagating, okay, just by satisfying that equation. Of course, that's the argument in here. Okay, so that's the propagation of a wave front wherever all these things are constant. A, K, omega. So then we're going to generalize this to the situation where these things are not all constant. Okay, I've got another picture here though. Let's see if that makes it even more. Well, what I just said. K dot R equals constant defines these surfaces, so the wavefront surfaces of constant phase. Okay, so we have it equal to 0, but if it equals to a constant, we still then have a constant phase of the whole thing. Okay, so that's actually an important comment as well. Phase, we'll even make this into a sentence. Define surfaces of constant phase which move or which propagate with speed c equals omega over k. So all those things were constant. Also an important note, k equals 2 pi over lambda. So you've got that inverse relation between k and lambda. Small wavelengths, large wave number. Okay, and vice versa. So large k corresponds to small lambda. Okay, I got a lot more here, but that's actually adequate. Well, why not? We add a little picture in terms of that dot product, just so we all have it here. So here's our direction of propagation. Here's our vector k. And say we have R right there. I'm just going to make, point out what that dot product then means. Okay. So then we have some angle theta, right? K dot R is equal to K R cos theta. And if that's constant, here you'll see a different color. That all of the KR cos theta, all of the K dot R along this red line have the same value, and that's what we need by a surface of constant phase. So yeah, we're explicitly using the fact that it's the dot product there. Okay. In addition, I have some stuff. Do we need this? Good. So we're going to leave that right there. That's enough. So now how do we generalize this? generalize this picture? Well, we have to go back and realize that C is not necessarily constant. So the question is, in this geometrical acoustics discussion, what do you do when the speed of sound is not a constant? So if it can vary throughout the medium. So next topic, or next in this progression here, what if C is not a constant, right? Because it's the derivative of pressure with respect to density, of course, throughout the medium, that derivative can be different. Okay? Density itself can be greater or smaller throughout a medium. So C is a function of R. Okay? C is actually, as I stated earlier, C is, generally speaking, actually a function of position. And yet these solutions here assume the constancy of the speed of sound. So what we do here then, could fill in a little more discussion on these notes here, what I just said, i.e. C is a function of position. So we got to belabor that point. And what happens to this situation here? We no longer actually have a solution of this exact form. Okay. So then we'll treat a sound wave as a plane wave only locally. Locally, that's the important point, so that A and K only change a very little bit. Change very little in regions, in a small region. Of size on the order of the wavelength. Okay. So this is where we're actually going to go down to the small wavelength approximation. So we're going to be very local, and so if we imagine the waves being very close together now, these wave fronts, and eventually they can veer off. So if you're up close here, then it just looks like plane waves, but if you stand back a bit, you can see that you veer off, okay? And so locally, your K is always perpendicular to these planar surfaces, but it gradually changes. But these things are no longer constant, which they were right here. So that's going to be the condition. And under these conditions, we can introduce rays. So now, introduce rays. The same thing would be for light ray or a sound ray, and that's given by what I just said here, right? It's perpendicular to a local wave front, but it changes gradually. And because of this, so we're going to erase this right here. Because of this construction, we can say that we're in the short wavelength limit. So these rays, and this is the short wavelength limit. Another way to look at it this amplitude would become a function of position. This wave vector would become a function of position if C is no longer constant. Did I say C up here? Yeah, if C is no longer constant. So there would be an approximation in which these are functions of position. In fact, if these were functions of position, you could go into the wave equation and you'd get some very long expression. It makes a good homework assignment. It's an alternate way of doing what I'm about to do. Let's see how much time I have to do what I want to do here. We've got nothing but time. Okay, so that's the discussion there. Good, let me send this up here. So I'm going to write down our standard solution and then the one we're going to modify. So one we've been working with is just C equals constant. We had phi equals A e to the I k dot r minus omega t. Now we're going to assume phi equals A e to the I times C. So this phase we're just going to represent like that right now. And assume that A here, we just use lowercase instead of uppercase, changes very little. Okay, changes slowly, because we're going to assume that it's essentially constant. Okay, changes slowly as discussed right here. So we're going to expand this letter C here. For a small region and a short time, small region in space, some very short time, we expand C. In fact, let's go ahead and do this. Because now the expansion to first order would be, you've got some constant, and you've got the gradient of C dotted into R plus the explicit time derivative deep C dt times t, right? So that's your linear expansion, a constant, linear in position, linear in time, okay? Plus higher terms that we're not going to deal with. So what happens though is this, we have phi is equal to A e to the I times this constant, which we're not going to worry about. Then we have e to the I times gradient C dot R plus deep C dt times t. And this is a small enough region, like said, so that's why we're going to treat A as constant. And now we can compare these two expressions. And by comparing these two, we can see that our gradient of C takes the place of K, and our deep C dt takes place of minus omega. Okay, I'm going to use this part of the board because I got a good space here. So next, define K equals gradient C omega equals minus dC dt. I need some more board. We'll keep the picture for the moment and just use this side. Still useful to be looking at that thing. Okay, so we're continuing on there. So K equals gradient C, omega equals minus dC dt. What do we know about a plane wave? In a plane wave, we have K squared equals omega squared over C squared. So since this is just like a plane wave really locally, okay, but now these are functions of position, we can just go into this expression. So here we have, right, deep C dx, y, and z, that's the K squared. So we have deep C dx squared plus deep C dy, C squared equals 1 over C squared deep C dt, the quantity squared. So this is a new differential equation. Okay, fantastic. So you see how that progressed. Okay, we just made this comparison with this local expansion. And you know, it's as local as you want it to be, because in other words, these can be as small as you want them to be, but this is what you're going to get. So this differential equation is called the Eichenall equation. Let me send this up, and then actually I have this side now. So we have a couple of definitions to write down, and then we can gather all of our results. Again, I better check the time. Okay. So let's put these things together. So we have B equals A, e to the I C, X, Y, Z, and T. This thing C is called, so this phase is called Eichenall, E-I-K-O-N-A-L, Eichenall. And the differential equation I just wrote can also be written, so we have it right there. We can also just shorthand, we can say it's the gradient of C squared equals 1 over C squared deep C dt squared. So finally, if omega equals constant, but C is not equal to a constant. So we can let omega be constant, but C not be equal to a constant. Then we have, for our Eichenall equation, gradient of C squared equals omega squared over C squared. And let me go ahead and erase this. And based on the definition, actually the definition I just erased, which is here, however, the Eichenall will now be C0 of x, y, and z minus omega t, right? Because its explicit time derivative is just omega. So this would be your ansatz, your trial solution, in which you separated off the time dependence like this, and then you'd have your differential equation for C sub 0, which is right here. Okay, it's non-trivial. If C is equal to a constant, of course it's trivial. Well, actually not trivial. If C is equal to a constant, though, it's just back to your wave equation that we've already done. If C is a function of position, then you've got some more work cut out for you. Okay, so that's the relation. Constant, we're back to what we have just studied. Okay. We obtained our previous results. But if C is not equal to constant, then we actually have to solve this differential equation here, and there's a relation as well. Yeah, now comes the punchline, but I'm running out of time. Let's see here. So if we can solve the Eichenall equation, it's just a nice short form of it, right? We don't have to write them all out, so it's gradient squared. If we can solve the Eichenall equation, then the surfaces of constant phase are just what we had before in our ansatz up there. Double star. Are given by this ansatz right here. Okay. The rays are parallel to gradient of C, because that was our K. So again, to do that little picture once again. I'm going to go a bit longer right now so I can put all this stuff together. Yes, we will. Let's see. Yeah, let's just have at it. So once again, this little picture, the idea that you had your surfaces of constant phase, that was a plane wave going just that way. But now what we have is surfaces of constant phase, right, where you get a subtle change of direction. And those surfaces of constant phase are given by this thing here because you've found this solution. It's no longer just the constant K. Okay? So, how to solve? I'm going to set up a chart here. And so when you write this down, I'm going to I'm going to split the board in half, and do two sides here, and it'll probably extend up and down both boards here. So this could be the better part of a page for you guys, but you'll never get this material like this right now. Okay, so how to solve this whole situation. This is the big surprise. Okay. So what we're going to do is a fluid mechanics column here first. Okay. And in fluid mechanics, this is what we have. Phi equals A e to the I. C equals constant. We don't care about gradient C dot R plus C dt times T. Okay. And then we find under that gradient of C is our K, and minus omega, or I'll make the other way around, deep C dt is equal to minus omega. Then we have kx squared, ky squared, kz squared equals omega squared over c squared, and I could even write that out, and I will. Because this is the actual relation. I could also just write grad c, but I'm writing it out for us this time. C dz omega squared over c squared. Okay. So that's what we have. Now this column here is called classical point mechanics, which is what we've been studying all semester. So what do we have in classical point mechanics that looks like this? We don't have this line here yet, but we have this. Okay. So in classical point mechanics, we have the following. We have gradient S0 equals P, yes. We have H equals, well, I'll write it the other way around, so I'm trying to make this exact. So we have ds dt equals minus H. We have px squared plus py squared plus pz squared is equal to 2m e minus u, and we have the Hamilton-Jacobi equation. S naught dy squared ds naught dz squared is equal to 2m e minus u. So far, so good. Missing something here? Well, actually, I'll put it in red here, because what do we have over here? We have C is equal to some constant plus C0 minus omega t in this case. And you know, I'll even ditch the constant just to make it look better. X, Y, and Z minus omega t. And what would we have over here? S equals S0 minus E times T, which is H, as we recall. Okay. So what we have, amazingly, is a complete analogy to the Hamilton-Jacobi theory. So that's what we're going to do. We're actually going to try to solve this for in a very important case using the techniques that we learned over here. So that's the surprise I was talking about earlier. Got a full analogy, and I think I'll finish up this discussion right here, just so we have it, although it's quite possible that I start this next time. Actually, I'll leave this here. What I'll do next time, I'm actually going to recreate this here and then continue on down. There's another important board. But just to wrap things up, right, we had that right there. So the left side is the short wavelength limit of waves where you can go to rays, and the rays are in the direction of gradient of C, which is perpendicular to the surfaces of constant phase. Okay? That's what you have here in acoustics, and formally we have a complete set of or a set of equations that just maps onto these if we were to rename them. Okay? And you'll remember this was the case where H, that is to say energy, is constant, and this case where we put the omega in down here is the case where the energy is constant as well. Not only that, we were saying that the right side of this equation is a function of position in the non-trivial case, because C is locally, right, dependent on, C is locally a function of position, C is a function of position. And over here, the right side is a function of position because the potential energy is a function of position. So we're going to use these Hamilton-Jacobi techniques, and we'll actually extend this chart. It's kind of interesting. We'll use those. And what we're actually going to use it for is to prove Snell's law and maybe another elementary type of problem. Okay, that's as far as we're going to get today. So like I said, next time we're going to write this up again, discuss it, continue the whole analogy, and then see where it leads us. Okay, good. That's enough for today. See you guys next time.